Today's presentation will be led by Professor Darcy Bullock. Professor Bullock is the Lyles Family Professor of Civil Engineering at Purdue University and serves as the Director of the Joint Transportation Research Program. Professor Bullock is a registered professional engineer in Indiana and has 25 years of experience in the industry, working closely with the state agencies, USDOT, and private sector partners. Professor Bullock's teaching, research, and consulting interest has been in the general area of transportation systems and implementation of advanced technology. He received a bachelor degree in civil engineering from the University of Vermont and a MS and Ph.D. in civil engineering from Carnegie Mellon University. Before we start, please mute your microphone for the duration of the presentation. You can ask your question by typing them in the chat window here in WebEx, or by going to menti.com and entering the code 88, 64, and 68 so that you can ask a question there too. Without any further ado, let's begin. Professor Bullock.
Thank you, Henry. This would have been a lot more fun to have done in person. We were looking forward to coming up to Michigan with that vehicle on the right. What I'm going to do before I jump in is just kind of talk a little bit about, and I hope the chat room has some activity during this telecon, but the overall message is, I think, vision of CCAT and many of the investigators on this project are that when we pull together government agencies, academia, and industry, that's how we're going to truly have an impact on the transportation industry. And before I introduce the team, kind of that so what message on why this is important from kind of a cost and environmental impact is if we look at the salt usage in the United States, and this is a graph that goes back to 1940s, and one of my colleagues, Debbie Horton, pulled this together for us. We kind of look at that use of roadway salt. You know, we're somewhere, I don't think maybe this past year, but we're somewhere north of 20 million metric tons of salt usage in the United States. And that has an environmental impact. There's a cost associated with that. One of the areas that there's some innovation in the winter operations space, and certainly do some of that up there in Michigan, and there's several other northern states, is instead of putting down granular salt where it may bounce off, we put down a granular material. And just to put down some numbers on why this is important, the salt is important for de-icing. A quarter of the crashes are associated with those winter conditions. We have a lot of injuries and fatalities each year due to winter conditions, and large proportion of state DOT maintenance budgets, and at least in the northern states, probably not Texas and Louisiana, are spent on winter operations, somewhere in the order of $2.3 billion. So what I'm going to talk about is the team that we put together, and I want to talk a little bit about the big picture vision, but the CCAT group has an educational mission as well, and I think I want to talk about kind of that staged approach on how we have built a prototype electric vehicle. And I think, and certainly Henry, I know you work in that space and several others on this call, is how do we provide those laboratory environments for our students and our staff to learn and develop connected and autonomous vehicles. And if you look at that vehicle in the background, that's a 6,500 gallon brine tanker that the Indiana Department of Transportation uses on interstate highways for applying the chemicals. And basically the idea is, how can we automate that application process so that we don't have distracted driving? We have lots of distracted driving laws and discussions in the US about people texting and driving, hands-free laws, but as a public agency, when we have drivers out there on the roads in congested conditions, we want them eyes on the road, hands on the wheel, and not having them distracted with switches in the vehicle. So that was kind of a little bit of a lead-in. This next slide talks about the research team, and I think the key point here is we had very strong participation by the Indiana Department of Transportation. Several of my colleagues are on this call: Jim Krogmeyer, faculty member in electrical engineering, Debbie Horton, Howley, Gijo Matthew, and Justin Malberg have all been integral partners. Gijo, I just want to thank particularly on this because he pulled a lot of these slides together for this, and we get into the Q&A on this. I hope everybody will, that's when we'll have a chance to do a, we'll probably pass some of the questions around to some of the other collaborators on this project. And then the other part of this is agencies set policy, set objectives. Universities are a good idea factory, but if we don't have strong partnership from the private sector, we're never going to get that deployed on the road. So we tried to take a very proactive approach by engaging a variety of the private sector stakeholders on this before we started the project. So, long-winded introduction, talked a little bit about the motivation, some of the existing technologies. But if we look at these two photos on this screen, the photo in the upper right-hand corner, that is a brine tanker going down the road applying the de-icing chemicals. This case, this was in advance of a storm. And the photo in the bottom right is the console. This happens to be for a plow truck. But if you look over there on the right-hand side, there are consoles with knobs and displays, and anything we can do to simplify that driver's workload is going to be not only improve the safety experience for the driver, our motorists out there on the road, but also make sure we get the de-icing chemicals applied where they should be. And as we look at this, I'll just point out this was a shot with a long lens, and it may look like we're closer than 300 feet, but we do have a challenge sometimes with people staying back 300 feet. So with regard to the existing technology, really what we tried to do here in this project was the agricultural, and I think we've talked about this many times at conferences and so on, many times the agricultural industry are a really good partner to look at to see some of the technologies that they've been using in the field in terms of what we can adopt to the highways, because they've been quite honestly a leader in some of this space. The major agricultural vendors have had things like auto steer and precision brine spraying for a number of years. And when we talked to the Indiana Department of Transportation about this, and we talked about, we had a little prototype and we had some mock-ups, and we said we'd like to look at this concept of adopting what they use in the field for applying chemicals to how we apply de-icing chemicals on the road. One of the operators looked at it and said, "Oh, this makes a ton of sense. On the weekends, my John Deere spraying equipment has exactly the same technology. This is a really good thing." So it was kind of interesting. Many times when you reach out to the maintenance folks, it's important to articulate to them that how it's going to benefit them and why it's worth the investment of their time. And it was just really exciting when we had a operator that not only was receptive to the technology, but kind of could make that mental leap in his head is he's already doing this in the fields. So a typical pre-treating activity that many agencies go through will be they will go out and they will pre-treat all their bridges, because the bridges oftentimes will freeze before the main road. So as you can imagine, and this is showing a 3-lane section of Interstate 465 in the Indianapolis area, and relatively light traffic conditions here, but that activity, particularly when you're driving in that far left passing lane and having to watch where the bridges are, turn on switches and turn off switches for the de-icing chemicals. There's two types of mistakes that you can make. One is you get distracted by the switches and you create an unsafe driving condition. Or the other situation is you get in a situation where the vehicles may be making some unintended movements into your lane, and you get focused on an evasive maneuver and you don't turn on and off the spraying equipment. So by automating that, you have the ability to make significant improvements in both of those spaces. And then the other aspect, as you're driving around, making sure you're building a map so you know what you've covered, because when you've got multiple passes out there, it is easy to lose track of where you've covered and where you haven't. So conceptually, this is probably the most complex figure I'll have up there, but basically it's a little flow chart, and it talks about, okay, is the tanker within the target zone? And if it is, so basically longitudinally down the road, where are you? And then the second decision there is, are you in that proper lane so that you're not reapplying, or is that a lane that hasn't been applied? And then you turn on the nozzles. There are some variations that we can do on that, and I'll talk about that a little bit. We talk about later on is we can spray some adjacent turn lanes. Now, what I want to do now is focus just a little bit. I've tried to introduce the big picture vision, but important part of our university mission is to make sure we train our students on how some of this, I would say, routine maintenance as well as some of this advanced technology works. So what we have done is built an electric GEM vehicle, and GEM just happens to be the provider we use. You could have put this on any vehicle. We picked an electric vehicle, and we put exactly the same GPS and telematics on the vehicle that we're going to put on 6,500 gallons. So we prototyped on this so we could learn our lessons on the mapping software before we went to scale. And if we look at the close-up of the vehicle, and again, we got some trade names in there. There are a couple different vendors that make precision spraying applications, but we got an interface in the cab. We got the GPS. We got the vehicle, and then we've got the brine vehicle. And this particular one for prototyping, we put individual controls on each one of those nozzles on the 4-foot wide boom, and that just worked as kind of a prototyping environment. And we had a couple different patterns that we could put down. The pencil nozzle, which is actually what typically Department of Transportation's use on their large trucks, and then we had a fan nozzle and a stream nozzle. And then the internal display provided a GPS map, and effectively you create recipe zones where those different colors on the screen talk about or show different application rates. If we look here, that's a display here on the left, shows all 4 nozzles on. Over here on the right, all 4 nozzles off. And then on top of the vehicle, these were the electronics. So the nice thing about this is we had a vehicle that students could drive in parking lots and on the sidewalk here. And in the summer, we didn't even put brine in it. We just put regular water so that we could do those lessons learned, teach them how this worked without putting them in, as you think about trying to put them in a 6,500-gallon tractor trailer, just the logistics of getting one person in the vehicle, coordinating with the DOT, getting that vehicle in and out of campus just was not feasible. So this gave us that hands-on experience to develop and test this. And I'm just showing you here a little video, and it's always a little challenging on webinars. I'm hoping you see the lower left-hand corner, you see the vehicle driving along, the nozzles turning on and off, and then in the upper right-hand corner, or upper left-hand corner, you see the trajectory of the vehicle going across the spray zones and the nozzles turning on and off with different rates. So what this did was gave us a nice environment for conducting not only training of the students, but we did several demonstrations of this with some of the stakeholders at the DOT and public agencies to show how this concept worked. And this just shows how those nozzles would turn on and off as they went over some of the areas that had been sprayed. And with the real-time correction on this, what we call RTK, we're down in that centimeter level type accuracy. And by doing that with water, we could, we'd put down a light flow rate. We could do these on hot days. 5 or 10 minutes later, we've reset, and we go back, and we can repeat the test. But what that gave us was an environment where we were using exactly the same control system on that pilot vehicle that we're going to be putting on the trucks for the DOT. And in fact, it's kind of interesting. The exact same vendor of the valves that we were using are exactly the same vendors of the valves that are used on the back of the truck. And what this really kind of turned into, and this is one of those magic moments when you kind of have the DOT partners and the private sector partners all kind of seeing the prototype and jumping in with both feet on how they can partner with the students and create a nicely engineered system where we have good buy-in, and it was just fun to kind of see this pride in ownership as a team pulled together. And this is a photo of the tanker just after they got the first deployment on it, about ready to go for a field run on it. And so this was the tanker before and then after. So before and after. And if you look, one of the things the INDOT partners did is they put on these left and right channels. So they had a center bar, and then they had a left channel and a right channel, so that as we're going by merging lanes, exit lanes, we could experiment. This is one where they sometimes do this with manual control, but again, it's a timing issue where those could turn on and spray sideways into the adjacent turn lane that they were going by. And you'll see the same equipment that you saw on the brine vehicle up there on the top of the tractor trailer. And this was the interface inside the tractor trailer. The same type interface panel and some switches. So features as they're going down, the automatic application. So I'm going to show you some of the tracking. It has the ability to have job sync, no double application. And I missed the video. Hang on, it didn't come up. Let me just try it one more time on the video. Didn't play. There it goes. Sorry. So this is going down the road, and we've got an overlay in the upper right-hand corner. And as we're getting ready to get in the spray zone, you see the spray going in and then turning off as we go over the bridge. And now underpasses, the same situation. You get shadowing with underpasses. Sometimes you'll get icy conditions because you're not getting the solar flux on the road. So you see as the vehicle goes under the underpass, it turns on and then turns off as it goes across the bridge. So hopefully those videos played, and I think the key parallels that you want to see there is what we demonstrated on the sidewalk, we were able to demonstrate on the road. In the future, we envision multiple versions of these, multiple vehicles out there, so it will be important to sync in the cloud, not just on the vehicle where they have been, so that we don't have any double application. I think this photo right here that Gijo has in there kind of shows kind of the level of precision that you can get with the vehicle in terms of turning on and turning off. Quite honestly, for highway applications, if we turn on within 10 or 15 feet of a bridge, that's good enough, but we still need that high-level RTK precision so we know which lane we're in. So longitudinally, we can be off 10 or 15 feet. That's not the big deal. But 10 or 15 feet laterally is the difference on which lane you're in. So one of the takeaways on this as we looked at this was that we really do need to have RTK in this. Future work will be bringing in some of the advanced telematics that we can put on the vehicle that bring off from the vehicle pavement temperature, chemical conditions of it, and several of these there's some Asheville Pool Fund studies on that are doing some work in this space that make some natural technology to integrate into this as those technologies that are identified in the Federal Highway Everyday Counts initiative mature. They're great candidates to integrate into this. So this vehicle that you see right here really is our living laboratory for the students that not only lets them try out the application, but also do some of that condition assessment during the winter months on campus. And so with that, this is probably, we've got to the point, I told my colleagues I'd keep it to 25 minutes. I've got some slides we can jump to if we got questions, but maybe this might be a good time for me to pause and ask for questions. So Calvin, did we have any questions come in on the chat room?
Yeah, I just got one here that just popped up. So it says it's very interesting study. They want to know if the flow rate of the automatic spray is it controlled according to the speed of the truck, or is the flow rate constant?
It's a really good question. So the question of it's critical that you have flow rate control based on ground speed. So the device measures ground speed so that we effectively have a constant application rate. So at higher speeds, the flow rate on the valves increases, and at slower speeds, the flow rate decreases. Good question.
Another one was, how long did it take to equip all this new technology onto the DOT fleets?
So you never want to ask those questions on serial number one, but I would say 2 to 3 weeks, and the period on that really was an issue of the truck didn't have a hydraulic pump. This was a system that they were bringing together for the first time with a new tractor. So 2 to 3 weeks, and that was really just time in terms of getting the plumbing and the hydraulics. in a perfect world, once you've got all those traps worked out, I think this would be a day of integrating the electronics on the truck and a day of integrating the valves on the back, and those could be done in parallel.
Great, thank you. Another one was, what is the estimated savings for adoption versus the upfront cost to equip all this technology?
Yes, that's a good question there in terms of cost to benefit, and it's the classic question of putting accurate cost-saving estimates on improved safety and improved quality. And so I'll toss that out. First of all, I think we're in a situation now where as agencies, we need to make sure we don't have driver distraction in the vehicle. I believe this is one of those technologies that we're going to just say this from a safety perspective of the driver and the motoring public. We don't want to have distracted driving in the vehicle. We need to do that. So I believe safety is going to drive this from an improved quality. And I think as we all drive around, we've probably seen, at least some of us that are geeking out on winter operations, we've probably seen areas where bridges have not been pre-treated when they should have been and along the same route, and we mentally probably make a note, they missed that. Well, generally they miss that because they might have been distracted by somebody cutting in front of them or something. So my belief is that this will pay for itself. It will be net positive in terms of improved safety and improved quality. We are still kind of grappling with that right way to do that. In any given year, there are a number of crashes with DOT vehicles involved in winter operations, and so we're trying to go through and extract out some of those nationwide costs for that, to quantify that. So good question, hard one to answer. I know I gave a little bit of a weaselly answer there, but everybody on the call probably understands that putting an actuary cost on safety and improved quality is always a little bit of a challenge. Over to you, Calvin.
So the next question is, they find it interesting in an application for a downtown setting, and they're curious how the GPS loss is in urban areas.
So good question on this. So in general, a long duration tunnel would be a big problem, and I'm just trying to think, Boston, Massachusetts, the central artery, that would be a major problem. In Indiana, none of our interstates are in what we would call an urban canyon. In a downtown CBD with 30 or 40-story buildings, that could be an issue. And what we're seeing now is more and more of these systems have an inertial component integrated into it. My assessment is for 97% of the DOT applications, probably 99% of the DOT applications, that is not a concern. For an urban area like Chicago, I would suspect that is an issue that probably needs some further work and is a project that me and my colleagues on the telephone call would love to get a research project lined up to integrate inertial navigation and to address that. Over to you, Calvin.
Great, thanks. The next one is the truck on a fixed route? And then what is the speed?
So in general, drivers are on fixed routes, and I'll make it really simple on this screen right here. One of the things is drive around the 53-mile circuit of 465 that has 3 to 4 lanes, and turn on and off for every bridge. So they are on fixed circuits. Speeds, generally speaking, are in that 50 to 55 mile an hour range. They don't want to create a moving incident out there, particularly when they get on that outbound lane, that far passing lane. They're traveling at a pretty good space. So if you do the flow rate calculations on there, there's a pretty good flow rate going through. Over to you, Calvin.
They kind of had a follow-up to that. They were thinking that if it was a slower speed, that it's possible it could be automated. Is that something that's being considered?
So you're really if you think about where my colleagues and I would love to go is before we start automating a tractor trailer that weighs 80,000 pounds, I would be much more excited about trying, or much more, I'd be a lot less nervous and more excited about automating a vehicle in a campus setting where we could have a safety driver. And I think that is going to be a really interesting area to look at, because these are some of the challenging conditions that connected and autonomous vehicles will go. So one of our visions, and that was one of the reasons we picked this electric GEM vehicle, is it has some capabilities for servo actuation of some of the drivetrain. And if you think about the agricultural space is already there pretty close with their auto steer, so that they minimize overlap and they control the flow rate. So it's on our roadmap. Before we put it out there on the interstate, I'm excited about trying to do this on a campus route.
So I think this is kind of touched on. There was a question about if the real-time guidance can be provided to the drivers when they're out on the road.
Yeah, so that would, what would the jargon term for that would be kind of job sync, right? And so as you can imagine, in the snow room, as you're managing the route, storms take different paths through the system, and you may want to redeploy assets to a different part of the network. So that is still an evolving area. I mean, right now, if you looked at it, the low-tech way that we do that right now is in the vehicle with a two-way radio, and they redeploy them. But longer term, I mean, it's almost the Uber or Lyft model for driving around, is that they're taking navigation maps coming in on the Raven. So instead of getting verbal messages over the state radio system, that screen up there, that's the screen in the vehicle there is giving them directions on where they need to go. And that is absolutely, when you think about a statewide call out in Indiana, I don't know what it is in Michigan, Henry, but 1,000 trucks just on the Indiana Department of Transportation, that's about 150 trucks per district. Automating some of that dispatch capability there is a huge opportunity for that.
Okay. I think we have one more question. Does it have any operating issues in the bad weather conditions, and can it be controlled fully remotely to avoid these conditions, supposing they have a good network and a control room facility?
Yeah, so one of the things in terms of, we were initially worried about the harsh chemical environment of the salt, and it was kind of funny when we went to the agricultural space on it. The valves that we're using are already used in the agricultural space, and the good thing is we've been able to build on the control valves that control the flow rate. Is the chemicals that are used in the agricultural space are already highly corrosive, and so the valves we thought would be the weak link in this, and what we found was agricultural community has done a good job on that. So as long as we do a good job with waterproof, chemical-proof electrical connectors, we've had no problem with kind of that automation from the cab. There's no, so that centralizing that, whether it's in the cab or in the cloud, is very easy. Over to you, Calvin.
Thank you. I think that's all we have. If anyone wants to get any last minute questions in before we wrap things up, please do so now.
Right. I don't think we have any other questions. So thank you everyone for joining us.